All right. We got 37 people in, so I'm just going to get rolling here, and then as people trickle in. For everyone joining the call, thanks for taking time out of your Friday afternoon. I'm excited to do a deep dive on query pruning in Snowflake. This will be posted up on our website later, so you have to drop at any point or get bored of me talking and want to listen later at 2x speed. Completely understand. We'll get that posted on our site shortly after the weekend when it's available. To set the stage for, let me quickly introduce myself before diving into the presentation. So for those who don't know me, I'm one of the co-founders and CEO of a company called Select. We're a SaaS platform that sole purpose is helping Snowflake customers optimize and manage their spend. So query pruning is naturally something that comes up a lot with different features we're building in our product, and many of the optimizations our customers are often applying. I'm based out of Toronto, Canada. For any other Canadians, hello. And hope you're staying warm today. And yeah, before starting Select, I used to work at Shopify and Capital One, where pruning came up in various shapes and forms as well. So excited to chat. Before diving into this, really want to set the stage for why this is why you should care about query pruning as someone using Snowflake. I mentioned this in the post I shared announcing this webinar, but after you've figured out warehouse sizing configuration and like what size warehouse your particular query is going to run on, the next most important technique from an optimization standpoint is understanding how micro-partitions and clustering works, which is where pruning comes in. We're going to talk later about the architecture of Snowflake, but when you often look at a query profile, you'll see that table scanning is the most expensive step in that query execution. So by having effective query pruning, you can eliminate a lot of unnecessary table scanning, which in turn speeds up your queries. Two big reasons why that's important. Probably one that resonates with everyone is that your queries run faster. So whether you're doing local development or building a BI dashboard, that's a great benefit. And then with Snowflake's billing model, where you're charged for the uptime of a warehouse, the less long your queries run and the less time your warehouse is up, the cheaper they become. So bunch of reasons you should care. Let's dive into talking about all this in more depth. So what I'm going to do today is start with a overview of Snowflake's architecture and the structure of their micro-partitions. That's really important to have like a mental model of how query pruning works. We'll then talk about the two different types of query pruning, static and dynamic, how you can actually check if query pruning is happening in your query, and then dive into a bunch of examples of like when it works, when it fails, which are kind of the more interesting ones to talk about. And then I'll share some general tips for employing query pruning in practice. Please jump in whenever with questions. I'll be keeping an eye on the LinkedIn chat. And if you want to ask something kind of midway through, let me know, and then I'll do my best to address that if I can. Okay, cool. Let's start with talking about the architecture of Snowflake. So for those who don't know, Snowflake really came into popularity due to this architecture. If you flash back to like 2014 when they came onto the scene, what they did that was really interesting compared to other traditional data warehouses was they separated compute and storage. Those were allowed to scale independently, which made Snowflake very easy to use and allowed you to add more compute without necessarily increasing storage, or more commonly vice versa. You could add more storage without being forced to pay for more compute that you didn't need. So the compute and storage separation is a big thing. Most people don't know there's like a third layer that scales independently, and that's the cloud services layer. This is something that's just kind of invisible that happens behind the scenes, but there's a bunch of stuff going on in here that Snowflake takes care of for all their customers. So things like access control, query optimization, the result cache, those all happen as like the first kind of entry point before your query even starts running on a virtual warehouse. So to kind of iron this point out or show an example in practice, I like to talk about what happens in the life cycle of a Snowflake query. So when you go and submit a query, here's you on the left, the first thing, as I mentioned, it does is it'll hit the cloud services layer. So Snowflake's going to do things like check if you have access to the specific tables you're trying to, or objects your query is trying to run on. It'll check if your query can be served from the result cache. And then crucially, it'll do something called query optimization, which we're going to talk more about today, where it's going to figure out the most efficient way to run your query. And part of that process of figuring that out involves figuring out what files you need to scan, which is where query pruning comes into play. And then there's some other stuff like transaction infrastructure management. Your query eventually goes and runs on one of the virtual warehouses, and it has to do this scanning of data over the network. And this, as we'll talk about later, is often the most expensive step of a query, because Snowflake has to go and fetch files from S3. So it's reading them over the network, even though it's in like your compute and your storage will be in the same region. It still has to go to that scanning over multiple different computers, which takes time. Then that information goes back to you. So to understand query pruning, we first need to build up a bit of a mental model for how storage in Snowflake works. So for this storage, we're specifically going to be talking about Snowflake native tables, not Iceberg, but I believe, I haven't dove too deep in this, it'll work in a fairly similar way. So Snowflake stores your tables in whatever cloud provider, in the storage service of whatever cloud provider you're running on. So if you're on AWS, they'd store it in S3. If you're on Azure, they'd store it in blob storage, etc. They take your tables and split them up into a bunch of files called micro-partitions. So whenever you hear micro-partitions, just think files, because they literally are just a file. Snowflake uses a proprietary closed source format that's like highly optimized and efficient for Snowflake's query engine. And one of the interesting things is they aim to keep these files around 16 megabytes heavily compressed. So the result of that is a big table, like if you have a table with, a terabyte of data or even hundreds of gigabytes, you can have millions of micro-partitions for a single table, which means doing queries or scanning, if your queries scan all those files, that becomes really expensive if it has to scan millions of files. For each of these individual micro-partitions, Snowflake will store a bunch of metadata for all of the columns in each file. So this kind of shows you a snapshot of some, but not all of the statistics that they would calculate for each of those columns. So this is like a hypothetical orders table. For if you had like a date field, they would store the min and max value of that date. So that can then be used later for query pruning, which we'll talk about in a second. So all of this metadata lives in the cloud services layer. This is this metadata storage kind of depiction I've shown. And there's kind of two really interesting things that does. The first one is it enables metadata only queries in Snowflake that don't need to run in a virtual warehouse. So if you've ever done like a select count star on a table or a select max of 2 columns, Snowflake can actually just find that information in this metadata storage without even sending it down to a virtual warehouse. So that's obviously awesome because it will effectively be a free query with caveats that I won't get into. And it is also just insanely fast. There are certain things that can cause this not to become a metadata only query. Like if you do anything that would need to be evaluated by during like the query execution. So if you did like a type conversion or queried on certain column types, it may not be able to answer that question directly from the metadata storage. So that's one of the things that this micro-partition metadata does. I'm not going to talk more about that, but I'll just kind of leave it out there. The thing that's most important, which is the focus of today's talk, is that this metadata enables query pruning. So first, I think it's good to define what query pruning is. Query pruning is the process of filtering data during different operators throughout the lifecycle of a query. So the main operators that happens in is in a table scan operator, but we'll talk about dynamic query pruning in a second, and that can actually happen through what's called a join filter operator. And what's happening during this step is in the cloud services layer. So when Snowflake is coming up with the plan for your query, it's going to look at the SQL you've provided. So we'll use this example where I'm selecting from the orders model and filtering on orders greater than, I screwed up the date here. It should be 2022, August 14th. When it sees that query come in, it can go look at the metadata because we've calculated what's the minimum and maximum date for each file or for each micro-partition. So it can use this information and say, we only care about files which contain values greater than this date. So knowing that, it can actually go and say, hey, only these 3 files contain records after August 14th, 2022. and therefore can skip scanning all these other micro-partitions, which in turn speeds up your query. So that's what query pruning is. Before kind of showing more examples of ways this can work and ways it cannot work, it's worth kind of defining what are the two different types of query pruning that can happen. So the first one is static query pruning. That is the example I just showed. So the thing to remember with static query pruning is the micro-partition elimination is able to happen during that query compilation step. So when Snowflake in cloud services layer is coming up with the plan of the query, it can check the metadata and determine what files need to be skipped. So that's why this is also called metadata-based pruning. And like most of the time when you have query pruning or elimination of micro-partitions in your query, it's happening because of this static query pruning. The other example, which is less common, but very cool once you know how it works, is called dynamic query pruning. Just like static query pruning, the goal here is the same. We're trying to eliminate scanning of files, aka micro-partitions, that don't need to be scanned for the purposes of the query. The difference between static and dynamic query pruning is that unlike static pruning, which happens at the compilation layer, dynamic pruning happens during the actual query execution. So if we look at this example here where I have a big orders table being joined to maybe a smaller customers table and a filter on like a country code of US, what Snowflake will do during runtime is it will say, hey, what is the list of customer IDs that live in that have country code equal to the US? And then it will create what's called a Bloom filter, which is just like a special type of filter that's really space efficient. And you can use that filter to try and do pruning based on that customer ID or based on this subset of customer IDs on the orders table. So it's kind of like the equivalent of building up like a where filter for the orders table, but during runtime. So I'll show kind of in more depth an example of where this can happen, which is during merge statements. So a lot of people use DBT. So I'm going to use this as an example. When you configure a incremental model in DBT, so here's an example using an orders model. This is a fairly vanilla looking incremental model. Under the hood, Snowflake will execute that as a merge statement. And the reason for that is because when you're doing an incremental model or an update to a table, you need to do it's a combination of a insert new records, but also update any of the records that already existed in that table. I should say Snowflake doesn't do this. Like DBT under the hood will convert this into a merge query or merge statement. And what's important about merge statements is they can often result in a full table scan. And the reason that happens is in order to figure out what records you need to update from your new batch of data, you have to go and look for all of those orders to see if any of the values have changed. So as you can see in this query profile here, we're scanning almost all the micro-partitions in this big orders table, which becomes the bottleneck in this whole query. One of the interesting things you can do is add a new date condition into the join, which will force dynamic pruning. And the way this works is because the orders table is not clustered on order ID, but it's actually clustered on order date. So if you remember before when I talked about that example, what does it do during runtime? It's going to take what are all the order IDs, and in this case, and all the order dates in this small table that we're trying to update the original table with. And it's going to take all those orders and then push those down into a filter. Again, it's like the equivalent of adding in a where clause on that big orders table saying only look at orders where the order date is part of these dates. And that just happens on the fly. So if you're using DBT, a very cool way you can actually go and force this dynamic pruning is by adding in a column which your table is clustered on. So the key thing to emphasize is you can't just add any column. It has to be a column that you know the table is clustered on. And we're going to talk about how can you know whether a table is clustered on a particular column and how you can get it clustered into that on that column if it isn't. Talk more about that later. But that's just an example while we're talking about query pruning that I wanted to highlight. So I already kind of hinted at this before, but it's very important whenever you're writing queries, especially after I show you all the different ways query pruning can fail. The kind of default rule is if there's any query that's going to be running a lot, either as a scheduled job or a DBT model or any thing, that's going to run often, you want to go and check that query pruning is working the way you expect it to work, so that your queries will run fast. So the most common way to do this is just by looking at the query profile. I showed before this partition scan and partitions total. Those are referring to those micro partitions I talked about earlier. So this is saying this table has 3,200 total micro partitions or total files. And this query is only scanning 5 out of those due to the condition, the order date condition we're putting in the query. So that's one way. You can also do this programmatically by querying the query history. So this is the exact same information I've showed, just rendered as a table. And then another interesting thing you can do if you're responsible for maintaining data sets for your entire company, you can look at a new view Snowflake released maybe a couple months back called table pruning history. So I have a sample query here. It may be a little hard to see, but these will be published after, and I'll probably pull out this exact query and paste it as a code snippet so you can grab it. But you can basically say, for a set of tables, I want to create like a pruning score. And I define this pruning score as how many partitions have we eliminated scanning. So if it's close to 100%, that means you're almost removing all of the query prunings, all of the partitions from your queries when they run, which is great for performance. So those are kind of 3 different ways you can check query pruning is working in practice. Okay, so I'm going to quickly run through examples of when query pruning will work. One of the things I want to call out, I posted this today when I was on LinkedIn when I was talking about telling people about this webinar. Most of the time, Snowflake's optimizer will just figure out how to apply query pruning no matter what you throw at it. So if you, again, put in like a hard-coded date against the orders table, that will just work. Again, assuming the table is clustered by created at. If you put in like an expression, so if you do like math on that date, it'll work as well. Even if you go in and do a subquery, so if you say, I want to filter on orders greater than the max created at timestamp from some other table, that will also work. And I can keep going. Like there's, as part of this talk, I try to come up with examples of where query pruning would fail by throwing more and more complicated SQL at Snowflake, and it would just figure it out. So if you do a CTE where you like calculate a value in one step and then reference that CTE in the next step, it'll still work. And same thing with multi-step CTEs. If you've ever been in a query profile and seen like step 1, step 2, in certain cases, Snowflake will recognize that this query needs to be evaluated as like a filter to be passed into the next query, and it will compute that value in a query that it runs separately and then apply that on the next in order to take advantage of query pruning. So as I mentioned, and then lastly, it also works for views. So here's an example view I made on top of query history. And if you then go and filter on that view, this will get pushed down to that base table and query pruning will go in action. Someone just asked, what if you typecast the left side of the query? It's a great question. That is an example where it can fail, and we're going to talk about that next. Okay, so as I mentioned, most of the time, query pruning will just work and you'll never have to worry about this. But there are some examples of when query pruning can fail. So one of those examples is when you're performing type conversions in the filter. So oftentimes when you, let's say, convert I don't know why people would do this in practice, but there have been some instances I've seen where people convert like a date to a string and then filter on that string. That can cause it to fail. Very similar example here where like the seemingly looks like you're filtering on a date, but because of this appending, this is a real example. I saw one of our customers' accounts, anonymized of course, but the kind of double pipe here and appending the string converts that value to a string. So anytime you're doing type conversions, it's always good to just check like certain things. I think someone gave an example in a column where you're taking created at and converting it to a date. That example that the person posted looks like it's a timestamp and converting it to a date, that actually works well. So not all type conversions will fail, but doing something like a date to a string will fail. Another key thing is the ordering of type conversions can also make a difference. So before, on one of the slides, I showed how if you do like a CTE and then reference that value of the CTE in the filter, it will work. In this case, it doesn't, because I'm performing the type conversion and then taking a max of that value. Snowflake has to do that, can only figure that out during query execution. So this will not prune. If you, however, change, so all I've done here, if you just jump between these, I've moved the date here to the outside. You first do a max of the end time and then do a date, then it will work. So super subtle, but these types of things can make a difference. Another example of something subtle is if you do a CTE, and instead of kind of filtering at that CTE in a subquery, and you just do a cross join to that, it's a common query pattern, that can fail as well. So the fix here is switching it to a subquery, and then it will work. So again, nuanced, but interesting things to be aware of. Another one is if you have a window function. So in this example, this is kind of like a conjured query that I'm not too sure why I do this in practice, but it does happen. If we have a window function that is computing some value, and even if I don't necessarily reference that window function anywhere down here, like you can see, I'm just filtering from this order CTE on this updated at field, this will still do a full table scan. And the reason for that is because Snowflake has to go and compute this new function, row or this column row num, on all the records before it can apply this filter. So that's another case. The way I didn't show how you'd rewrite this, but the way you would is push this filter up to the filtering of the raw table, so that it happens before the right after or during the table scan step before the row number is being computed. I don't know why I have animations on the slide, but another interesting example of when pruning can fail is when the tables become less well clustered over time. So in all the examples I've shown, we've assumed that the table is well clustered on whatever column that we're filtering on. We're going to talk more about later how you can check if it's well clustered on that column and how you can get it into that well clustered state. So what can often happen to users is they've manually clustered a table at one point in time, and then gradually over time, that table becomes not well clustered. This effectively, the easiest way to think about this is think about your data getting jumbled or less sorted over time. It's kind of two big cases where this can happen. One is if someone is going in and updating records in the table. So yeah, if they do a big like batch update that ends up reprocess or updating a large portion of records in the table, then that can cause clustering health to decay because the data is no longer well sorted. Another very interesting example is with late arriving data. So if people have heard of a company called Fitbit or Whoop, like these wearable devices that people use to track health metrics, something that's very common that happens with these is your device goes offline because your battery died, or maybe you like choose to stop wearing it for like months at a time, and then you turn it on again. When that device comes back online, it's going to go and emit all those records to Snowflake or to their cloud and then load it into Snowflake. And what happens is you kind of have nice orderly data arriving in your table. So you could say it's naturally clustered by a device event timestamp. And then all of a sudden, these old devices come online and you start loading in data that was actually from months ago. So as a result, these new micro-partitions are getting polluted with older data, and pruning becomes less effective because if you think back to this diagram I showed way at the beginning, let's see if I can get back to it. Yeah, if you think back to this diagram I showed here, think of your table in Snowflake as like a spreadsheet that you keep appending new records. So if all of a sudden this like latest batch of data contains a mix of all these values from a single day plus old data, when Snowflake goes to do that static query pruning, it says, oh, we actually can't, we have to scan all of these partitions because they may potentially contain some of the dates that we care about. So couple different ways you can get around the late arriving data. One is the simplest is just reclustering the table, which we'll talk about, periodically reclustering the table, which we'll talk more about later. So that's another big reason that pruning can fail. Some other reasons I'll call out is if you're working on, if you have like a JSON column or semi-structured data column, Snowflake will actually, it's pretty incredible. They will go and collect the same metadata for all of the elements of that semi-structured data. So if your JSON column has like a date and an ID and a bunch of other columns, it will go and collect metadata for those columns, just like it would a regular column. So it's kind of converting your JSON column into a tabular one. And then pruning will work. There's a few exceptions though, where they don't collect metadata and therefore static or pruning won't work. And that's if a single element has null values across any of the records, they won't. Another is if that column has a varying data type. So for example, let's say in one row, you have an ID that's a number, and then later on it becomes a string. They won't collect metadata for that varying data type. And then also if that column is ever missing from certain rows, they will not collect metadata for it. So any of these cases are scenarios where pruning won't work as well. So always be careful of that. I don't think this is frequently used across Snowflake customers, but for the handful of customers who are using things like dynamic data masking, that will break query pruning if you try and filter on a column that has dynamic data masking applied. And that's because the policy gets applied at the query runtime. It can't be evaluated in advance during the compilation step. It has to check on the fly, does this column satisfy this condition, which causes, again, pruning to fail. Two other examples that I'll quickly call out. One is like user-defined functions or external functions. So if you have a function that has to go fetch data over the network, Snowflake can't know in advance if that will result in certain files not having to be scanned. Another example that, or another, I'll say area, I don't have a specific example, is when you're using complex expressions. So I read about this. I need to go reproduce a proper example, but I believe you have like a certain number of filters with like a lot of ORs involved. That can screw up pruning apparently. So I think the overall mental model I'll leave you with is think about scenarios where it would be hard for Snowflake to know in advance from the column metadata which files would be filtered out. And those are cases where it won't be able to do that, figure that out up front, and therefore pruning won't work. The other thing I'll call out that Niall just pointed out to me in the chat is Snowflake is constantly improving their query optimizer. So if I were to give this, if I had given this talk, like, I don't know, even a few years ago, a lot of these examples I gave with like CTEs and subqueries, it probably wouldn't have worked. So they've consistently been updating their optimizer to handle all these different cases. So take what I say as a point in time snapshot of what is true. It may not be true months from now if you're watching this video. So, one of the lessons as well is just always go check the query profile to see if it's working as expected. I can see someone in the comments has pointed out that JSON for JSON columns, there's a max of 200 or maybe for metadata collection, there's a max of 200 elements. So if you filtered on one of the element 201 or 300, you may not get query pruning working. That is interesting. I did not know that. So another thing to keep in mind when you're doing things with big JSON columns. Okay. What I'm going to talk about next is like taking everything we've talked about and with query pruning and putting it into practice. So if you're going and writing a query and you want it to prune well, one of the first things you need to do is figure out how your table is clustered. So a couple different ways you can do this. And this will vary based on the organization, but one of the easiest things to do is talk, and I recognize this will be hard at certain companies because you have no idea who made this data set, but at smaller companies, definitely doable. You can talk to the creator. So you can ask them, have they applied sorting a certain way, or have they enabled clustering on a table? If you don't know who that person is, you can go and check the table definition. So Snowflake will have you'll see the automatic clustering key will be set. And that will, in almost all cases, mean that that table is very well clustered by that field. And you can go use that in queries. If you don't know who a creator is, but you have access to a code base which contains the definitions for that table, you could go look and see, is there like an order by statement on the column? Or if you know about the data ingestion process, like if it's event data that's batches are being loaded each day, you may know that the data is naturally correlated with some column, like an event timestamp, that'll then be clustered on. And then the last thing you can do when in doubt is you can run the system clustering information on a column, which will spit out how well clustered the table is on that column. So this is actually something for our customers who are using our product. It's something we released maybe a month or two ago that's really cool, which basically just goes and calls this clustering information across all of your columns in a table. So in our UI, you can quickly jump in. And if you're trying to answer this question of, hey, if I'm querying this query history enriched data set, how should I actually go and write my query so that it can take advantage of how this table is clustered? And what you can see here, we've come up with a clustering score, which just translates the output of this system clustering information command. It translated into a more readable output. So the interpretation of this is any column with 99% or this high clustering score means it's a very good candidate for query pruning. Meaning if I go and filter on one of these columns, like start time greater than 2 weeks ago, I'm going to get really good query performance. We were shocked. This has been really helpful. Even this screenshots from our own account. We had no idea. So we built this data set and we clustered it by start time, because we often in our web app will filter on show me all queries in this particular time period. And we had no idea that we thought all of our queries had to just filter on timestamp in order to take advantage of query pruning. But from this, we actually learned, oh, you can actually filter by end time, or even the most surprising one was query ID. Somehow that Snowflake has, and I'm assuming that it's because they have a similar use case internally, they've made it so that query ID is highly correlated with start time, or can be filtered in a way that enables query pruning, which is really cool. So oftentimes by running these analyses, by looking at how your table is clustered with this clustering information function, you can discover new ways in which your table can be queried very efficiently. So once you figure that out, you then need to go and actually filter on that well-clustered column in one of your queries. So this is just showing an example before of like the different ways you can do that. You can also do it in the dynamic query pruning example I showed, where if you have a join happening, you can try adding in a join condition on this column that's well clustered, which can force query pruning. Once you've done that, again, because there are these edge cases, we always recommend you check the query profile to make sure it's working as expected. So you can go in and look at it. Something I want to caveat is that the same kind of applies to any type of optimization you're doing to a job. Don't just do this for like a one-off query that you're never going to run again, where it doesn't matter if you actually go and sped it up. Like your time is much more valuable than figuring out how to speed up this job that doesn't matter or may never run again. So first, kind of understand what could be the value of making a certain query run faster. If it's going to go into a dashboard that a business user or executive looks at, and you want it to be performant, that's a great use case for making sure query pruning is working the way you'd expect. And then what do you do if your table or your column is not in a well-clustered state? I don't want to spend too much time on this because clustering is like a whole other topic that probably deserves a separate presentation on, but there's 3 different ways you can cluster in Snowflake. One is natural clustering, which is based on how the data gets inserted into your table. 2 is automatic clustering, where Snowflake takes care of keeping your table well clustered. So most of the time this is great. It can get expensive. So it is something you have to monitor. There's specific scenarios where, like, if you have a really large table that's getting frequently updated, the automatic clustering service can have trouble keeping up with those updates and basically be running all the time. Again, this is one of those things that This may even be less true of today. I know Snowflake's been making a ton of investments in improving their automatic clustering service to make it more cost effective, but it's just something to keep in mind. So yeah, we'll talk more about natural clustering, but it's effectively free. And then manual sorting is when you, in your query, add an order by statement to like sort that data. So think about that spreadsheet, you're sorting it prior to creating that table. So we'll talk about these a bit more in depth very quickly. One is natural clustering. So again, think back to that Fitbit example, or even like any website which has event tracking. Every day, new batches of data are going to be coming into that table. They're most likely going to have some timestamp in common. So if you're thinking about like events or orders, there'll be like an event timestamp or a order created at that for that batch of data that was generated on that day or yesterday is going to be very similar. So over time, each time Snowflake, you go and insert one of these batches, it creates a file for that batch of data. So your micro-partitions will naturally be clustered, think sorted by this date. And therefore, if you filter on one of these dates in one of your queries, Snowflake will know like, hey, we can ignore all those micro-partitions because they only contain old data that the query itself does not care about. So that's natural clustering. Automatic clustering, the second one I mentioned, is a background service that Snowflake maintains. They use Snowflake Managed Compute to resort your data behind the scenes. So you don't need to worry about figuring out like how to update a query. You just tell it, hey, I'm going to filter on this certain column a lot in the future. So I want it to be well clustered by that column. I'm going to tell Snowflake to cluster my table by that column. And you then will get charged a small amount based on how much work Snowflake has to do in the background. So again, as I mentioned, this will be a factor of how big the table is and how frequently the contents are modified. I think earlier this year, Snowflake released a function you can call that's very similar to this. Very similar to this system clustering information command. I think you can call like system estimate automatic clustering costs or something like that. If anyone has the link and can share it in the comments, that'd be appreciated. You can use this in advance to see, if you're at this stage where you're like, okay, I actually want to recluster my table by this column. How much would that cost on an ongoing basis? You can call that function and check, how often that, or how much that would cost on an ongoing basis. There's a good question on any rules of thumb on cardinality. I don't have a hard number or rule of thumb in my head, but for people who are curious, the thing that this user is bringing up is, I can't see the username, so I apologize. But when you have a column that has a ton of cardinality, meaning lots of unique values, it can become very difficult and more expensive for this automatic clustering service to try and sort those values into the same micro-partitions. So a common example where this comes into practice is Snowflake recommends don't cluster on a timestamp. You should cluster on a date instead. So imagine this created at was a timestamp and not a date. You could cluster on created at semicolon, semicolon, date. So you could cast it to a date and it means it's going to cluster on the date instead of the timestamp. So I don't, to the person who asked the question, I don't think there's like a magic rule of thumb of like, if this column contains more than 100,000 unique values, then don't cluster on it. It's one of those things where you have to experiment with. Actually, something you can do that I just remembered is you can use that system estimate automatic clustering cost function, and you can pass in different values and then see how much it would cost. So you can use that as a rough rule of thumb or way to kind of understand how cardinality could affect your automatic clustering costs. Okay, and the last one I'll call out is manual sorting. So if you have a job which creates a new table each time it runs, this is a very common pattern. It's like a CTask query. One of the really cool things you can do is you can just add an order by at the very end of that table definition or SQL statement. And what that does is, if you look at your query profile, you'll see a sort step at the very top, right before that data gets written to the table. So again, think just like a spreadsheet. You're telling Snowflake to lay out your data in a certain way so that each of those micro partitions contains data with similar values. Okay, cool. That is everything I had. Happy to take more questions. While I'm waiting for questions to come up, I will just do a quick product plug. So for those who don't know anything about Select, we're a SaaS web application. Our sole purpose is to help Snowflake customers optimize and manage their Snowflake usage. We provide a lot of very in-depth views into what's going on in your account, different ways you can optimize, improve performance and spend. So if you're interested in learning more about that, you can go to this link, select.dev/demo. You'll just see my calendar appear on there. So that will actually book some time with me. I'm more than happy to chat about the product or things outside of the product. If you're just curious to chat more about Snowflake, always happy to discuss the topic. So thanks a ton for everyone coming out. I will give you all back some time for the rest of your Friday afternoon, and don't hesitate to reach out in the future if you have any questions. If you have feedback on this or have like other topics that would be you'd like to hear about with respect to Snowflake, let me know, and I'd be happy to try and do something on them in the future. So thanks so much and have a great weekend.